Welcome back to ECE 501B. Homework number 5 is due tomorrow. Today's Wednesday. No office hours because of homecoming on Friday, but I do have office hours tomorrow morning from 9 until 10. Homework number 6 is due on Monday, and then a week from today is exam number 2. And we will talk about that, but essentially it's the material sense exam number 1 that will be covered, and maybe the first part of chapter 7 on adjoints might be included in exam number 2, but that's about it. So maybe some of today's won't be on there. But the project, I've created 2 different drop boxes, and hopefully I have the dates correct in this class. I don't on the other class, so I have to change that, meaning I think I posted it in October and it's already past due in the other class. But I think this one is correct. Deliverable number 1 is really just a communication between you and I about what you want to do for project 1 and an approval, so to speak, and then outcome number or deliverable number 2 is the main part of your project. Deliverable number 3 is a reflective paragraph on what you learned or how you benefited from the project. Today what I want to do is continue with chapter 7 material, which concerns operators on an inner product space or on inner product spaces, since we actually have to have multiple inner product spaces when we start talking about these adjoint operators. And we'll talk about, or maybe just review slightly, the linear functionals. But if we do have a linear functional, we can actually find a vector W that will provide us with an inner product that does equal that linear functional. And if it's a linear map, remember that we have these 2 properties that govern a linear map, and that's additivity and homogeneity. We'll also begin really with an example of an adjoint to give you this feel for the adjoint. It's a linear map, but now it's really sort of going back where we began, meaning if we begin with a linear map that goes from an input space to an output space, the adjoint is a map from the original output space, now that's the input space, back to the original input space, which is now the output space. Can I be any more confusing on the adjoint? But it's really a way to slide the operator between the slots, having that adjoint available. And we'll show that the adjoint map is linear, which means that it needs to satisfy these 2 properties, additivity and homogeneity. We'll talk about the relationship between the map and its adjoint in terms of the range and null space and how they are related, and we'll show that, and then you can essentially do orthogonal complements to some of those lines of equivalent statements to achieve the additional lines. And the matrix representation, one way that you can think about this is if you have a linear map and its matrix representation A, then the adjoint can be shown to be the complex conjugate transpose of the original matrix representation of the linear map T, which is the matrix representation of the adjoint. And then we will talk about what it means, or what we have when we have a self-adjoint operator, or when the map is equal to its adjoint, and what does that imply in terms of relationships. The linear functional then that we are dealing with, here I've switched and now we have this unique vector U instead of maybe earlier I was calling that a W, but Theorem 42 in Chapter 6 tells us that if we start with a linear functional, if we want to now convert that really linear functional into an inner product over our vector space capital V, then we can create, or we can build or find this vector u in our vector space capital V that will produce the same output as our linear functional phi sub u. And we build that by first finding an orthonormal basis of that vector space V. Those are the E's, the E1 through E sub n. And then we apply this linear functional to each of those orthonormal bases. That's what the phi sub E1s represent, or the phi sub E2s. We conjugate that scalar and use that to weight or scale each of the orthonormal vectors E1 through E sub n, and that gives us our vector u in the vector space capital V, which we would then have fixed in this inner product. And if we wanted to find the linear functional's value applied to an arbitrary vector, little v, then we could simply use this inner product and this vector that we've now built. And that's actually a fairly powerful way to now convert an arbitrary linear functional into an inner product on our vector space. It takes an orthonormal basis on our vector space and then the creation of this unique vector little u. Now that we have this way of building these linear functionals, we can also start talking about an adjoint for a generic linear map. Here we have a linear map T that goes from an input vector space V to an output vector space W. The adjoint of T, which we call T dagger, now goes from W back to V. But again, it's a linear map. And it's such that we define that adjoint to allow these inner products. And what's the result of an inner product? A scalar. We take two vectors and produce a scalar, and on the left we have an inner product space, and on the right we have a different inner product space, but the two of those inner products produce the same scalar. And we then use that relationship to define our adjoint, which again is a linear map from W back to V, which means that the inner product on the left is working on what vector space concerning its inner product, if that made any sense. That one you're dealing with this vector space capital W, and on the right everything is ending up in the vector space V, which has an underlying inner product defined on that. And a high-level view, or one way to think of an adjoint, is to just say, oh, having an adjoint allows me to really slide or move this linear operator. It's not a, I should say, a linear map, T, because it's not necessarily restricted to being a linear operator. The linear map T from the first slot to the second slot. If you needed to have that particular linear map in the second slot, then you would have this adjoint of your original linear map T. So let's look at a quick example of where we can now create or build an adjoint, and let's do it for a linear map that goes from R3 to R2. What did we call such a linear map before? Do you remember the terminology we were using? So even higher level than whether it's injective or surjective. In this case, could this map be surjective? Could it be surjective? And I had to look at it again. It can be, can't it? Because it's going from a higher dimensional space to a lower, so you could fill up R2, but you wouldn't be able to it's not an injective map by definition, really, because now we're going from a big or a higher dimensional space to a lower dimensional space. So you know you have a non-trivial null space. But this we were calling a dimension reducing map, weren't we? I think. So we're going from 3 to 2. We're reducing the dimension. That's not that important, but I'm just trying to get us sort of communicating or thinking back to what we've already seen before. Let's define that to be t. It's now working on a 3 vector. Let's call each of those components or coordinates in the 3 vector x1, x2, x3. And let's just say that our linear map then takes and produces the first coordinate of the output in R2 to be x sub 2 plus 3x sub 3. And the second coordinate, let's let that be 2x sub 1. If that's now our linear map, which is a dimension-reducing linear map, what do we know about the adjoint T-dagger? What are its input vector space and output vector space? It now needs to really go the other direction, doesn't it? It now needs to go from R2 to R3. And this one you know can't be surjective. The other one could be, it wouldn't have to be surjective, but you know this one can't be. And this one might be injective. It might have a trivial null space, but you're not guaranteed of that necessarily. So let's now try to create T-dagger. We already have been given the linear map T. Once we've been given that, let's now try to find T-dagger. Or to create that, to create T-dagger, let's go ahead and pick a vector in terms of labeling it. Let's pick a vector W in our input vector space for this adjoint map to be in capital W, or let's now let W, for obvious reasons, be y sub 1, y sub 2. No obvious reason there, but I'm just picking y1 and y2, and we know that that now lives in R2. And what we want to do is pick that adjoint to satisfy the defining relationship for the adjoint, which we know is, if I now have V T-dagger W, what does that equal by definition of the adjoint? I'm actually writing it backwards from what I've been writing. I usually write this as the left side. Now I'm putting it on the right side, and my right side I've now just put on the left side. So this now needs to be TV, comma, W, that inner product. So now let's build. We know what TV is. We just defined that. That's this linear map. And so we can now use that, but let's maybe, before I do that, I'm actually going to go ahead and write down what the left side looks like. This now says that I have x1, x2, x3. That's now my vector V times T-dagger y1, y2. This is now my W. But I know that that's equal to this piece. So that's now equal to, and I know, well, let me go ahead and write this down. I have T applied to V, and that's supposed to then be comma W, but let me go ahead and expand that out to be y1, y2. And now let's go ahead and perform the linear map T on that vector x1, x2, x3. And by definition, or what we said it was, the first coordinate is x2 plus 3x3. So this is now going to be x2 plus 3x sub 3, and the second coordinate was 2x sub 1. And we want that to be then inner product with w, which is y1, y2. If we're dealing with real vector spaces, we're now in R2. How do we form the inner product? These are just two vectors in R2, and we want to form the inner product. How do we build that? What's this answer? We just do the coordinate-wise multiplication and add those up. Are we good with that? That's just the definition of the inner product. Let's now go ahead and distribute the y1 through that first piece to produce x sub 2 y1 plus 3x sub 3 y1 plus 2x sub 1 y sub 2. But we now want that to actually equal that piece. So we now need to somehow pull out x1, x2, and x3 and have that now create. So let me say that we now have that equaling x1, x2, x3, inner product with T dagger y1, y2. Meaning, let's now order that in a way that we can sort of explicitly see what x1 scales, what x2 scales, and what x3 scales, because the result of T dagger y1, y2 needs to be a 3 vector, and whatever it is going to be what is multiplied by x1, x2, x3 coordinate-wise. Or, let me now take this piece, there's an x1, and write that as x1 times 2y sub 2 plus x sub 2 times y1 plus x sub 3 times 3y1. All I'm doing is rewriting that second line in this particular screenshot so that I can explicitly pull out the vector x1, x2, x3, or make it easier to do, and now that is supposed to equal some inner product on these 3 vectors. And so what goes in the first coordinate of the right in the second slot of my 3 vector? 2y sub 2. What goes in the second slot? I'm sorry, the second coordinate in the second slot vector. And the third coordinate in the second slot's vector is 3y1. And that, by definition, is actually supposed to be the adjoint of T applied to y1 and y sub 2. Which now says that T dagger y1, y2 goes from R2 to R3 in the following way. It takes y1, y2 and maps that to 2y sub 2 in the first coordinate, y sub 1 in the second coordinate, and 3y sub 1 in the third coordinate. And that's now the linear map of the adjoint. And we built that by simply using the definition of the adjoint, by equating these inner products. And that's now a dimension raising linear map. It's going from R2 to R3. That's the adjoint of the original map, T, which we started with. T went from R3 to R2. Its adjoint goes from R2 to R3. Now let's look at some properties of that. That was just an exercise to show how you can actually create or build the adjoint based on the definition. That's now an example or maybe a concrete way of sort of thinking, what's this adjoint? Well, it's just a linear map. But it now goes from R2 to R3 for that particular example. We want to now address this question, is the adjoint a linear map? And one way to answer that is to really ask two separate questions. What two properties does a linear map have to satisfy? Additivity. And now that you've stated that one, you should automatically know what the next one is. Homogeneity. So let's see what it does with additivity. Suppose we start with TV and we then have this addition of two vectors in the second slot. How can I rewrite that to maybe create two different inner products? Or now, well, really I'm just trying to split up the W1 plus W2 and make two inner products. And what do I know about the additivity property of the second slot? Does it change anything? Is it okay? It's just goes through straight, doesn't it? So the additivity of the second slot allows us to then write TV inner product with W1 plus TV inner product with W2. But now what if I applied or utilized the adjoint definition of each of those two inner products on the right? How would I rewrite those two terms on the right, those two inner products, using the definition of the adjoint? Then the first one would be V, T dagger W1, and the second one would have the same structure. It would be V inner product with the adjoint times W2. But now let's just go back. Let's now utilize the additivity of the second slot, which allows us now to say, oh, V is inner product with T dagger W1 plus T dagger W2. But if we now look at this piece and applied the definition of the adjoint to that, so now that left-hand side I've highlighted in yellow, but the left-hand side is equal to what expression if I applied the adjoint to that? Is that okay? But now, what does that imply? Now I can equate what's in the second slot of those two inner products. Meaning now I can see that I've demonstrated the equality of those two inner products. V is in the same, it's in the first slot in both, and now I can say that, oh, T dagger applied to the sum of W1 plus W2 must equal T dagger W1 plus T dagger W2. And does that look like an additivity property? Yes, so we've shown that the adjoint does enjoy an additivity property. Let's do a similar investigation for homogeneity. With homogeneity, we can now say, let's say that we now have TV inner product with a scaled version of a vector W. And what happens if I want to slide that scalar applied to the second slot outside the inner product? Now I have the conjugation of that second slot, don't I, scaled. So I now have the second slot conjugtivity, and so I now have, or the conjugate homogeneity of the second slot is maybe what I've said before. That's now TV inner product with W. What if I now apply the adjoint definition to that inner product on the right? And now what if I slide the scalar into the second slot? So now I have to conjugate the conjugate again, so it now ends up as A, T dagger W. But again, if I look at what this would look like if I now applied the adjoint operation to that, or now I have this left-hand side is equal to, using the adjoint definition, what does that equal? Is that okay? So I've just used the definition of the adjoint to move the linear map from the first slot to the second slot, but that now allows me to say, oh, I can see that I have an inner product with V in the first slot, and what's in the second slot, those have to be equal. So now I can conclude T dagger AW is equal to A T dagger W, and that's now the homogeneity that I was looking for. I now have the adjoint map enjoying additivity and homogeneity. I've now shown that the adjoint map is a linear map. Thus, T dagger is a linear map where, in general, if our linear map T is taking the input vector space V to the output vector space W, then T dagger is going to go be a linear map from W as the input vector space to V, the output vector space. Let's look at some other properties that the adjoint enjoys or satisfies. One is additivity. If we have two linear maps that we add, S plus T, and we take the adjoint of that sum, then that's equal to the sum of the adjoints. And that's true for all S and T that map from V to W. We also have conjugate homogeneity. Meaning if we scale a linear map T and then take its adjoint, we can push the adjoint operation onto the linear map, but we now have to scale that by the complex conjugate of the original scalar A. Or this is now A star T dagger. And that's true for all scalars A and linear maps T mapping from V to W. What happens if we take the adjoint of an adjoint? By that I'm meaning, what if we have the adjoint and we take the adjoint of that? What would be your guess? Pardon? It's just T, isn't it? So that's now getting us back our linear map. So now you're essentially going, if you sort of, maybe to think about this, you want to go back to that previous example and now derive from the adjoint, go and take the adjoint of that and see what you get in terms of the linear map. So it's similar to what happens when you take the transpose of a matrix. These are linear maps, not matrices. We're not looking at yet the matrix representation of this, but now you're essentially going to the output space with T, but that's not what you're doing. Now you're starting in W and going to V, and now you want to go from V back to W. Well, that's now the original linear map T. So T being a dimension reducing map is just one example, but you now have T dagger was now a dimension increasing map. And now you reduce that back with the adjoint. So, and you haven't lost any information, so to speak, in performing that particular operation. And it's one easier way to sort of think about that is that's consistent with doing a transpose of a matrix. You transpose a matrix and you transpose it again, you get your original matrix back. But these are now linear maps. What would happen if I would take the adjoint of the identity map? That better give us the identity map back. And the last one that we will introduce is what happens if we now take the products of linear maps, meaning if we now had a linear map T and then we applied the output of that, or we took that as the input to a new map S and took the adjoint of that, now we have to, it's similar to inverses of a matrix. Now we have the reverse order. We now take T dagger, S dagger, and that's equivalent to then the adjoint of the product of two linear maps. And that's true for T, taking us from V to W, and S being a linear map from W to U. Those are now properties of adjoints. Let's look at a connection between adjoints and linear maps. And I don't want to hear your interpretation of interesting or useful, just accept that. So now we'll just say there is an interesting or useful relationship. Obviously that's up for interpretation, but let's just accept it. So that there's now a relationship between the null and range space of the linear map T and its adjoint. And this is given to us in Chapter 7 with Proposition 7, and this is then labeled null space and range of linear map T dagger. And this actually has 4 different parts. If we have a linear map T taking us from an input space V to an output space W, then we can make the following connections. The null space of this linear map T dagger is actually equal to the orthogonal complement of the range space of T. Let me write that out fully. So we take the range of the linear map T and we find its orthogonal complement, and that actually is equal to the null space of T dagger. So some of these may be easier to find, or maybe you're starting with the linear map T. You can now find the orthogonal complement to that, and that's now giving you the span of the null space of T dagger. That's the first statement. The second statement is that the range of T dagger is equal to the orthogonal complement of the null space of T. The third fact is that the null space of T is equal to the orthogonal complement of the range space of T dagger. And I promised there would only be 4 of these. The fourth one is that the range of the linear map T is equal to the null space of T dagger's orthogonal complement. And if you look at this, for example, what happens to 1 and 4? How are 1 and 4 related? Maybe you should just interchange one of those left sides and right sides with each other. Let's say we take number 4 and interchange the left and right. Then we have the range of T on the right and the orthogonal complement of the null space of T dagger. They're just orthogonal complements, aren't they? So 1 and 4 are really connected. What about 2 and 3? Same thing, right? So let's just show that 2 of these we can verify, and then we would just have to take the orthogonal complement of those to verify the other 2. So really, you can think of 2 of these are sort of giving us new information. The others are just working in the orthogonal complement of those original results. Let's now look at the first one and see if we can demonstrate or prove that that's actually true. So here, this one is saying, let's show the equivalence of the null space of T dagger and the orthogonal complement to the range of T. So what's the orthogonal complement of the range of T? If I said, here's a linear map T, what would it mean to be the orthogonal complement of that range space, of that linear map? It's not quite the null space. So there's 4 subspaces for a matrix, and you can sort of think about that for a linear map. You have a linear map because T could be doing funny things with dimensions. It doesn't have to be an operator. So let's say that T was mapping maybe from R2 to R5. So what dimensional space are you dealing with for the range of T? R5, let's say. So now, let's say that it only spans, how much can it maximally span in that R5 if it was going from R2 to R5? It can only give you 2, at most, 2 linearly independent vectors in the range space. So you now know that the range space is living in R5, but it's 2-dimensional. What's the orthogonal complement's dimension? It's 3, but what space is it living in? R5, right? And that's different from anything with the null space. The null space would be living in a R2 space if we have a non-trivial null space. Do you see why it's not the null space? It's actually the orthogonal complement of the range. You also have the null space of T and its orthogonal complement. So there's 4 different subspaces that you can sort of envision that result from any linear map. And now, the first one, we're dealing with the orthogonal complement of the range of T. So if you just think about that example that I just gave, you now have, what's the dimension of that right-hand side? Do you remember? Please help me. We had the range space was 2, right? And we were living in R5, so the orthogonal complement was 3-dimensional. It's in R5. Is that okay? So we need to show that the null space of T dagger is that same space for whatever that is. But now we're going, I was looking for my eyes. I don't need to have my eyes. Let me just worry about my tablet, okay? You guys are just a blur. You're in my null space. Not in my orthogonal complement to the null space. Now, let's go on. So what do we need? We need to now, let's pick a W, and let's say that that lives in the null space of T dagger. We now have a vector W that's in the null space of T dagger. We now know that if I have T dagger and I apply it to W, what's going to happen? If W lives in the null space of T dagger, what happens when I apply T dagger to W? Do you get anything? It's in the null space, so actually W maps you to the 0 vector, doesn't it? That's by definition. That's how we define W. So now let's just say, okay, you have the 0 vector. I can build the 0 vector with this operation, T dagger applied to W. Oh, really? Okay, well then let's say the 0 vector is V inner product with the 0 vector. But what's that second slot? Another way of rewriting that second slot is T dagger W, correct? Since T dagger is going from W to V in our terminology. So now we could say, well, that implies that we could say V inner product with T dagger W is equal to 0. And what V is that true for? Which vectors are orthogonal to the 0 vector? All vectors. So this is true for all V. So this is for all little v in the vector space capital V. But what's the definition of the adjoint allow us to say about that right-hand side? So now we know that if we have T dagger, then we must have TV inner product with W equals 0, and that must be true for all V. That's the definition of the adjoint. So this is true for all little v in capital V. But where does W live then? If W, when inner product with TV, and this is true for all V in the vector space V, so where is TV going to put you? Well, in terms of where are you going to end up, how do I want to ask this question to make the answer clear? If I now say, here's a vector, and take it through this linear map. Oh, here's another vector, and take it through this linear map. Here's another vector, and take it through this linear map. What are you finding after you take it through the linear map? You're finding the range of that linear map, are you not? But so now in the first slot, we are covering the range of our vectors of that linear map T. Yes, that's our first slot. We're filling up the range, but now what's happening to W? It's orthogonal to that, isn't it? W is orthogonal to everything in the range of T by that inner product statement. So we're saying that the range of T's orthogonal complement is actually where W lives. Is that clear? So the first slot says we're finding the entire range space of the linear map T, but that inner product tells us that W is orthogonal to that, meaning W lives or is an element of the orthogonal complement of the range of T, because it's producing 0 for the inner product. And now we just have to remember what we assumed initially for W. W, we said, was in the null space of T dagger. But now we've just concluded that W is in the orthogonal complement of the range of T. Those have to be the same spaces. Therefore, the null space of T dagger, which was the first way that we picked W, is equal to the orthogonal complement to the range of T. And that's what we were trying to show. Let's look at the third one. We know 1 and 4 are the same, effectively, because they're just orthogonal complements of each other. And if we can show 2 or 3, then we've got the other one. So let's look at 3. So number 3, let's pick V, and this is going to look very similar to what we just did, so we won't spend as much time. Let's now pick V in the null space of T, And what can we now say about the linear map T applied to V? What does that give us? That's the zero vector again. And now we can do the similar thought process that we had before. Now we can say, oh, let's start with 0 and inner product that with W, and what do we know that must equal? The 0 vector is orthogonal to everything, so we know that's equal to 0. But we now know how another way of rewriting the 0 vector, that's just TV by definition of V. Or we now have TV, inner product with W, is equal to 0, and which W's is that true for? That's true for all W's, isn't it? Because any W is orthogonal to the 0 vector. This is now for all little w in capital W. Again, let's do the definition of the adjoint. And that now allows us to state what? If we now have TV inner product with W equaling 0, what's the definition of the adjoint tell us about the next inner product? And which W is that true for? By definition of the adjoint, that has to be for all W again. So this is true for all little w in W. And what does that tell you about V? Where does that live? Well, V is somehow orthogonal to T dagger W. But what's T dagger W produce if we're hitting it with all W's? T dagger W is not quite a null space. Now I have a W, don't I? And now I'm throwing it through T dagger. So what's that going to give me relative to T dagger? That's the range of T dagger, right? If I'm hitting it with all my W's, now I'm exploring, you give me a W, somebody else give me a W. Now we're filling up the entire T dagger range space, but where is V then? It's orthogonal to that. So now we have V living in, or an element of, the range of T dagger's orthogonal complement. But where did we begin with V? V was in the null space of T. So now we've shown that V, we didn't change V. It was in the null space of T, and it's also in the orthogonal complement of the range of T dagger. And we've now been able to show that the null space of T is equal to the orthogonal complement of the range of T dagger. And I'm going to say that we're essentially finished because we can now take orthogonal complements of those two results to demonstrate the other two statements. Or taking orthogonal complements of both sides of the remaining entries completes the proof. Now, let's look at what happens when we start looking at matrix representations of these linear maps and the adjoints. There is a useful relationship between the matrix representation of a map and the matrix representation of its adjoint. And that's actually proposition 10 in chapter 7. Suppose that A, and this is sort of a collective A, this A includes all of the vectors in an orthonormal basis. I'm just going to say that's A. So if A is an orthonormal basis, on an underlying vector space V, and one that would be very easy is just the standard basis. That's an orthonormal basis. So if A is an orthonormal basis on V and B is an orthonormal basis on W, then the matrix representation of T dagger from an orthonormal basis B to an orthonormal basis A, vector space, is the conjugate transpose of the matrix representation of the linear map T from an orthonormal basis A, that's the basis of our input vector space, to a vector space B, which is the output vector space. And we won't go through that, but let's just sort of remind each other what we mean by complex conjugate or conjugate transpose. What if I gave you the following matrix, A, B, C, D, E, F, and hopefully no one's out in the hallway listening to our lecture. They're going to go, I thought this was the university. He's just doing the ABCs. We now have A, B, C, D, E, F, so we went more than the ABCs. We doubled it, so we've advanced. But now if I give you that, what's the conjugate transpose of that matrix? And A, B, C, D, E, and F can all be complex scalars. What does that look like? Well, we just have to follow what we said it is. It's the conjugate transpose. So let's conjugate each scalar individually. We would say A, B, C, D, E, F, and we would conjugate those. That's the first part, the conjugate, and then we would transpose it. So that now we end up with A, B, C, D, E, F, and all of those are conjugated. That's now the conjugate transpose of a matrix that's 2 by 3. We now have a 3 by 2 that's each entry is conjugated. And we could then just say that we transpose the matrix representation of T and then take the complex conjugate, or we could do it the other way. We could take the conjugate and then transpose it. Transpose the matrix representation of T and then take the complex conjugate or vice versa. Let's go through some examples. We started with examples. Let's take another trip down example lane. Adjoint example 1. Suppose that now T is a linear map from C3 to C3. And suppose that T is our linear map, and the three coordinates are x, y, z. And let's say that this linear map now takes x, y, and z to the following three coordinates. It's going from C3 to C3. Let's say the first coordinate is 2x plus 1 minus I, y. The second coordinate, let's say, is 3 plus 2i, x minus 4iz. And the third coordinate, let's say, is 2ix plus 4 minus 3iy minus 3z. And we actually want to find the adjoint of that linear map. Well, the way that we are going to do it is maybe cleaner than the first example we talked about today. We could take an inner product and try to find the effective three coordinates of T dagger. But we now know something about the matrix representation of a linear map and its adjoint. They're related by a complex conjugate transpose. Meaning, let's now find the matrix representation of this linear map, take the complex conjugate transpose, and then pull that back into a linear map, and that will give us T dagger. That's what we want to do. That's the example. Meaning, the first step in this process will be to find the matrix representation of the linear map T, and let's call that A. And if that's the case, what's the first row of A look like? What's in the 1, 1? Well, how big is A? It's 3 by 3. Our matrix is square. And we're now dealing with the top row. What's in the 1, 1 entry of that 3 by 3 matrix? One by one, 1 is 2, but oh, you want that to be the scalar. Yes, okay. I thought maybe you were answering my 1, 1 and saying 1 plus 1 is 2. No, I'm teasing. So this is 2. What's in the 1, 2 entry? 1 minus I. And what's in the 1, 3 entry? Nothing. 0. Now let's populate the second or middle row. Is there anything in the first column? 3 plus 2i. Middle column, 0, and the third column. And finally now our third row has a full complement of entries. It's 2i, 4 minus 3i, and minus 3. And what did we just say? Well, we now know how to find the matrix representation of the adjoint of T by simply taking the complex conjugate transpose of the matrix representation of A. Let me write that down. So now we have the matrix representation of T dagger is now the complex conjugate transpose of A, and let's just write that down. The diagonal doesn't change, and I now can put the 1 or the 2, 1 entry in the 1, 2 place conjugated, I now have 3 minus 2i, and I have a minus 2i in the 1, 3 slot. In the 2, 1 slot, I have 1 plus I, and in the 2, 3 slot, I have 4 plus 3i. In the 3, 1 spot, I have 0, and in the 3, 2 spot, I have 4i. Are we okay with that? Because I'm going to slide it away. But this should look like the conjugate transposed of A. And now what I have to do is pull this back into our traditional linear map. Meaning if I now said build T-dagger using X, Y, Z, what would the first coordinate be equal to? Now I simply really put X, Y, Z as a column on the right of this matrix and say, what's my first coordinate going to be? It's going to be 2x times 3 minus 2iy plus minus 2iz. That's my first coordinate. So I have 2x plus 3 minus 2iy minus 2iz. Is it clear where that came from? And now I can write down all the others. Now my next coordinate is 1 plus ix plus 4 plus 3iz. And my third coordinate is now 4iy minus 3z. And maybe that wouldn't have been very easy to build if we would have gone through the inner products and trying to find relationships between the first, second, and third coordinate in that inner product expression. Let's look at another example. Are there questions on that? So now we've gone from a linear map T and found its adjoint by using this matrix representation relationship of those being related by a complex conjugate transpose. Let's look at another example. In this example, let's suppose that T is a linear map from R3 to R3, and suppose now we have T of x, y, z equaling 2x plus y in the first coordinate, 3x in the middle coordinate, and 4y minus 3z in the third coordinate. And now this is trivial, isn't it, in a sense, building up the matrix representation or creating the matrix representation of that linear map T. You know it's square. We're going from R3 to R3, and what's in the top row? 2, 1, 0. What's in the middle row? And the third row? And now you can immediately write down the matrix representation of the adjoint. In this case, we take the conjugate and transpose it, and how hard is the conjugate going to be? That's going to be pretty easy, isn't it? Since they're real, we don't have to worry much about that. And this is now the matrix representation of the adjoint. We just need to transpose it. And I can copy down my diagonal. Transpose doesn't change that. And did I do it right? I have a top row of 2, 3, 0, a middle row of 1, 0, 4, and a third row of 0, 0, minus 3. now we can say, what is T dagger of XYZ? The first coordinate is 2x plus 3y. The middle coordinate is x plus 4z. And the third coordinate is minus 3z. And if you really enjoy playing with matrices, we could check our work if we wanted to. What if we decided to just sort of do it with a simple check? This isn't a proof, but it just sort of allows us to think about what we've just done and try to understand these relationships that we've been talking about. T now is this linear map from an input vector space to an output vector space. And in this example, this second example, what's a vector V's dimension? It's 3, isn't it? It has 3 coordinates. Let's just make that 1, 1, 0. And how big is the, or what are the dimensions on a vector W in capital W? 3 also. Let's make those a little different. Let's go, that's 0, 0, 1. Using those two vectors, let's now find the inner product of TV with W. So what's TV? Well, T was 2, 1, 0, 3, 0, 0, 0, 4 minus 3, and you can check my work tonight, because I know you probably go home and study your notes very thoroughly. Now what do I do here? Well, that V vector is convenient. I'm just adding the first two columns together in T, leaving me with 3, 3, and 4. And if I now take the inner product of that vector with W, and W was just 1s in the second and third entry, so I'm just going to scale the second and third entries of TV and add them together, and I'm scaling them with 1s. So I'm saying, what is the inner product of 3, 3, 4 with 0, 1, 1? And that's too easy, right? That should be 3 plus 4, or 7. And now let's go the other direction. Let's just look at what happens if we took V and took the inner product of that with T dagger W. Our T dagger, and now I'm maybe sort of abusing notation, that's really the matrix representation of T dagger, is 2, 3, 0, 1, 0, 4, 0, 0 minus 3. W was 0, 1, 1. Again, this pulls off the second and third rows added to, or columns added together, and I have 3, 4 minus 3. And I now want to take the inner product of V with T dagger W, or I'm now taking V, which was 1, 1, 0, inner product with 3, 4 minus 3, and what do I get there? I again get 7, and that's what I was wanting to show, that my definition of the adjoint of these equalities of inner products does give me the same scalar, 7 in both cases. Now let me introduce one new concept, and that is a self-adjoint operator, to give you something to think about over the weekend. An operator T and now that we're dealing with an operator, we know that it is mapping from V back into itself, is self-adjoint or you might hear this called Hermetian, and now you can just go home and be saying Hermetian, Hermetian. It's just a fun word to say, right? So all weekend you can start saying that word. You now have a Hermetian map if the linear map T is equal to its adjoint. And what do we know now about some of these, or this relationship? What do we know about T if it's an operator? It's square, right? Its matrix representation is square. And we know then that the matrix representation of T dagger is square. So we'll have to find out now what that means relative to what we just talked about in terms of the matrix representation of a map and its adjoint. The complex conjugate transpose of those, and now we're saying the matrix representation of T must equal the complex conjugate transpose of that matrix in order for it to be self-adjoint. So we'll stop at that. Your head is now spinning, but you now have this Hermetian map, which means that T is equal to its adjoint.